What if you could look at an apple and not just see that it's red, but actually see its sugar content, its ripeness, or even spot a bruise hiding just under the skin? Well, that's the power of hyperspectral imaging. It's this incredible technology that goes way beyond what our eyes or even a normal camera can perceive. It reveals this hidden world of chemical information that's all around us. Okay, let's dive right in.
So to really get what's so revolutionary about this, let's just compare two cameras. The one in your phone, it sees the world in just three basic color channels, red, green, and blue. It just mixes those together to make a picture. But a hyperspectral camera, well, that's a whole different beast. It captures light in hundreds of super narrow, really specific bands, way more than our eyes can ever distinguish. See, every material reflects light in its own unique way across these bands, creating what's essentially a spectral fingerprint. So we're not just talking about color anymore. We're talking about seeing what something is fundamentally made of.
All right, so here's what we're going to cover in this explainer. First, what it really means to see the chemical world. Then, we'll get into how the technology actually works, the different ways you can scan something, how to make sense of all the data you get, and finally, where this is making a huge impact in the real world.
So let's kick things off with the core idea behind hyperspectral imaging, or HSI. It's a technology that completely shifts our idea of a picture, moving it from just simple pixels into the world of molecules.
Just think about that question for a second. What if, instead of just taking a picture of a farmer's field, your camera could actually map out the soil moisture, tell you exactly what kind of plants are growing, and even spot crop stress days before it's visible to the naked eye? Well, that's exactly what HSI does. It turns a normal visual scene into a quantitative chemical map.
So, how does it do that? How does it work? Well, the magic is really in how it combines two really powerful technologies into one single system.
At its heart, HSI is a form of what's called chemical imaging. It smashes together the spatial awareness of imaging, which tells you where something is, with the incredible analytical power of spectroscopy, which tells you what it's made of. So for every single pixel in the image, you're not just getting a color, you're getting an entire spectrum of data that acts like a chemical signature.
And the result of one of these scans is something called the hyperspectral data cube. I want you to imagine a giant stack of hundreds of images. The X and Y axes are just your normal picture, right? But that third dimension, the depth of the stack, is wavelength. So if you pick a single pixel on the top and just drill down through that stack, you're tracing the complete spectral fingerprint for that one specific point. It's pretty cool.
Now, building that data cube isn't a one-size-fits-all kind of process. There are actually three main ways to scan a sample, and each one has its own pros and cons.
So you can think of them as three flavors of HSI. You've got whiskbroom, which is super meticulous and scans just one point at a time. Then there's staring, which looks at a whole scene at once, but cycles through the different wavelengths one by one. And finally, you have pushbroom, which scans a single line, but gets all the wavelengths for that line at the same time.
Okay, so each method has a trade-off. Whiskbroom gives you incredible spectral detail, but it is so slow, which makes it best for lab work. Staring is great for things that aren't moving, but you might lose a little bit of spectral resolution. The real workhorse of the industry, though, is pushbroom. It scans line by line, kind of like your office scanner, and that balanced approach makes it absolutely perfect for industrial settings like doing quality control on a fast-moving conveyor belt.
But capturing that massive data cube, that's really only half the battle. The next step, and it's just as important, is figuring out how to turn all of that raw data into something you can actually use. Real insight.
And to give you a sense of the scale here, get this. A scan of one single tiny wood chip in one study generated 3,600 individual spectra. That is an immense amount of data to work with.
And of course, buried inside that massive data set, there are challenges. A huge one is dealing with optical noise. The number one culprit is something called specular reflection. Just think of it like the harsh glare you see on a really shiny object. That light just bounces right off the surface without ever going into the material, so it carries zero useful chemical information and can totally corrupt the data for that pixel.
And this isn't just some minor annoyance. As the source material points out, this glare can severely distort quantification. In other words, if you don't find a way to deal with these shiny spots, the final chemical map you create could be just plain wrong. So getting the lighting and the camera angles just right is absolutely critical for good data.
So how do scientists fix this? They use a field called chemometrics. You can think of it as the special data science toolkit for HSI.
It's a bunch of really sophisticated algorithms that can clean up the raw data, correct for things like that specular reflection, and then use some fancy analysis to pull out the hidden chemical patterns from that enormous data cube.
So the workflow for the data analysis is a pretty clear 4-step process. First, you capture the raw data cube. Step 2, you clean it up and correct for all that noise. Third, you apply some powerful analysis to simplify all that complex data. And finally, step 4, you generate a chemical map that you can actually read and understand. Now, I know this all sounds incredibly technical, but the real power of HSI, the really cool part, comes alive when we see how it's being used to solve actual problems out in the real world. This is the why this matters part. From the factory floor all the way to the farm, HSI is quickly becoming an essential tool for quality control. It allows industries to go way beyond just spot checking a few samples here and there. Now they can analyze 100% of their product in real time without ever touching or destroying it.
And the applications are just so diverse. In pharmaceuticals, it's used to spot fake medicine. In agriculture, it's making sure our food is safe and high quality. It's a key technology for sorting different plastics to make recycling way more efficient. And in medicine, it's even being used to help researchers get better at identifying cancer cells. Let's look at a concrete example. The problem for a drug company is making sure every single tablet is perfect. A counterfeit could be really dangerous, and if the active ingredient isn't spread out evenly, the dose might not work. HSI is the solution. It creates a detailed chemical map of the tablet, which can instantly flag a fake or show a manufacturing defect that would be totally invisible to the naked eye. Or how about food safety? How in the world do you find a tiny piece of plastic or one unripe berry on a production line that's moving thousands of items a minute? A person could never do it, but a pushbroom HSI system can scan everything in real time. It can spot foreign materials, check for ripeness, and even see bruises under the skin, making sure only the best stuff makes it to the store.
And that right there, that's the crucial point. The old way of doing quality control meant pulling a small sample off the line to test it. HSI completely changes that entire paradigm. It gives you non-destructive, detailed chemical information for every single item, for 100% of the product. That's a whole new level of quality assurance.
So when you boil it all down, its value comes from this incredible combination of 3 things: the speed of real-time analysis, the accuracy you get from chemical fingerprinting, and the total coverage of 100% inspection.
And this brings us to one last, really fascinating question. For the first time, we have a practical way to see the detailed chemical makeup of the world around us, and we can do it in real time. So if we can now see the invisible, everything from the health of a single plant to the composition of a distant planet, what hidden truths, what new discoveries are just sitting there, waiting to be revealed?